Okay, we're just going to continue on, do more examples, and just see how we can use the unit step function to solve differential equations in Laplace transform. So in this example, we're going to have a battery, and the circuit is going to have some resistance. We'll assume that is 8 ohms. It's going to have some capacitance. So this is an equivalence. And then we're going to assume that there's 1/4 farad in the circuit. And initially, we're going to assume there's no charge, 0 coulombs in the capacitance. And for the voltage, we're going to assume that initially it's at 2 volts. And then at 6 seconds, it turns off and goes to 0. So we can write the voltage as being 2 if t is less than 6, and then after 6 it drops down to 0, which means we can write this as in terms of unit step functions, as it's initially 2, and then it's going to switch off, so we're going to subtract 2 after t equals 6. So I'm going to write my v of t in that form. All right, so now if we start there, we're going to assume the current goes in that direction. So as I go across the voltage source, I'm going to have a gain in voltage of v of t. As I go across the resistance, I'm going to have a drop in voltage of R times the current. The current is the derivative of the charge. And then across the capacitor, it's going to drop Q over C. Now I'm back to here, and that's going to equal 0. So what does that mean? So I'm going to have, for my v of t, I have 2 minus 2 times the step function, t minus 6. My resistance is 8 times q prime, and then I'm going to have q over 1/4 is 0. So let's clean that up a bit. So I'm going to leave the 2 minus 2 times the step function at t minus 6 alone. I'm going to add 8 times q prime to the left, and I'm going to both sides. I'm going to add q over 1/4, but that's the same as plus 4q. And now I know that the Laplace transform of q prime is going to be minus q of 0 plus s times the Laplace transform of q. But q of 0 is 0, so I'm just going to be left with s times the Laplace transform. That should be of q. All right, so now what do I have? I have Laplace transform of 2 minus 2 times the step function at t minus 6. It's going to be 8 times the Laplace transform of q prime plus 4 times the Laplace transform of q. And we just saw that this is going to be s times the Laplace transform of q. So we have Laplace transform of 2 minus Laplace transform of 2 times the step function at t minus 6. It's going to be 8s times the Laplace transform of q plus 4 times the Laplace transform of q. So let's rewrite that. I have the Laplace transform of 2 minus the Laplace transform of 2 times the step function at t minus 6 is 8s times the Laplace transform of q plus 4 times the Laplace transform of q. I want to isolate this, so I want this to be something times the Laplace transform of q. So I'm going to factor that out. And that becomes what? 8s plus 4. Laplace transform of 2 is going to be 2 over s. Now I'm going to use my properties of this. So notice there's no t here, so I don't have to mess around with that. So I'm going to get 2 over s times e to the minus 6s. And I want to solve for the Laplace transform of q. So Laplace transform of q, then I can divide both sides by 8s plus 4. So I'm going to get 2 over s divided by 8s plus 4 minus 2 over s times 8s plus 4 times e to the minus 6s. This is a problem. I don't know how to deal with this. So I'm going to do the partial fractions thing. And fortunately, I'm going to get 2 for 1 because that's exactly the same thing. So if I can do partial fractions on that, I'm going to be fine. Just like before, I would like this to look like s plus a, because that's what my transform tables look like. So what do I have? I have 2 over s times 8s plus 4. I'm going to multiply top and bottom by 1/8 to get rid of that. And if I do that, I'm going to get 2/8 on top. And multiplying this 1/8 through, I'm going to get s plus 4/8. So that's going to be what? 1/4 over s times s plus a half. And now I can do partial fractions on this. 1/4 over s times s plus a half. And note, this is equivalent to this term here and this term here. So I can use this in both of those. It's going to be a over s plus b over s plus a half. So I'm going to multiply both sides by this denominator. That'll give me 1/4 is a. The s's cancel. I have s plus a half plus b. And the s plus a halves cancel. So b times s. So let's let s equal minus a half. Get 1/4. I'm going to 8 times 0 plus b times a half. So b is 1/2 if I multiply both sides by 2. If I let s equal 0, I'll get 1/4 on the left. And I'll get a times 1/2 on the right. So a is going to be equal to 1/2. Made a mistake. That's a minus 1/2. So this should be a minus 1/2 for this s. So that's a minus a half there. So that means that 2 over s times 8s plus 4 is going to be a over s, be 1/2 over s, minus plus a b over s plus a half, which is going to be minus 1/2 over s plus a half. So plugging that into here, I now get Laplace transform of q is going to be 1/2 over s minus 1/2 over s plus a half. And I can do that inverse Laplace transform on that, no problems. Minus the quantity. Now this is going to be the exact same thing. 1/2 over s minus 1/2 over s plus a half times e to the minus 6s. And I note that the Laplace transform of 1/2 is going to be 1/2 over s. So that's no problem. This looks like the Laplace transform of 1/2 times e to the minus 1/2 t. Because that's going to give me 1/2, which goes there, over s minus a minus 1/2. Because of this term, I'm going to have to evaluate at t minus 6. And I'm going to be multiplying the step function evaluated at t minus 6. Okay, so this part is no problem. It says that q is going to be 1/2 minus 1/2 e to the minus 1/2 t. For this term here, I'm going to have 1/2 times the step function at t minus 6 minus 1/2 1/2 e to the minus 1/2, but instead of t, I'm going to have t minus 6, and then I multiply by the step function at t minus 6, like so. This is a mess. This is a lot. On a quiz or test, just leave it like that. There's no point in simplifying that. You're just going to make it more likely you make a silly mistake, and just run with that. Okay, let's do another example. So this example is going to be really nasty, kind of messy, but it's going to kind of show this issue of what happens, that you have to evaluate it at t minus 3. Suppose I have the following differential equation. Excuse me. I want to take a Laplace transform of this thing. The problem is my properties of Laplace transform says that the Laplace transform of the function evaluated at t minus a times a step function at t minus a is going to be e to the minus as times the Laplace transform of the function. This thing does not look like it's in the form of t minus a. In this case, a is 3. So I need this to be, everywhere I see a t, I really need to see t minus 3. So how can I deal with that? So I've got my t squared. So everywhere I see a t, I'm going to subtract 3. But if I subtract 3, I have to add 3. And so now this is exactly equal to what's above there, but it's in terms of t minus 3's everywhere. So now if I FOIL this out, we have the t minus 3 squared plus 6 times t minus 3 plus 3 squared, or 9. Okay. Now I can deal with this in terms of what that looks like. So this becomes y prime minus y is equal to the quantity t minus 3 squared plus 6 times t minus 3 plus 9 times the step function at t minus 3. And my f of t minus 3 is the t minus 3 squared plus 6 times t minus 3 plus 9, which means my f of t is going to be t squared plus 6 times t plus 9. Right? So if everywhere I see a t, I replace it with t minus 3, I get this, which is going to be equal to that term up there. Now I can use this property, and I can deal with the Laplace transform. So I'm going to take the Laplace transform of the left. It's going to be equal to the Laplace transform of the right. And at this point now I can just grind everything out. So this becomes Laplace transform of y prime minus Laplace transform of y. Now here again, this is some function given by t squared plus 6t plus 9 was evaluated at t minus 3, which is exactly what I want here. So this becomes e to the minus as, in this case a equals 3, times the Laplace transform of f. So let's rewrite that. Laplace transform of y prime minus Laplace transform of y is e to the minus 3s times the Laplace transform of t squared plus 6t plus 9. It's minus 3s. And I know that when t equals 0, y is equal to 2. Oh, no, I said 1. Sorry. Looking at the wrong place. So y of 0 is 1. So this is now minus y of 0 plus s times the Laplace transform of y minus the Laplace transform of y. It's going to be e to the minus 3s. Laplace transform of t squared is 2 over s cubed. Laplace transform of 6t is 6 over s squared, and the Laplace transform of 9 is 9 over s. And then y of 0 is 1, so I can add 1 to both sides. So I get s times the Laplace transform of y minus the Laplace transform of y is equal to 1 plus e to the minus 3s times 2 over s cubed plus 6 over s squared plus 9 over s. I can factor out a Laplace transform of y, so I get s minus 1 times the Laplace transform of y is 1 plus e to the minus 3s times 2 over s cubed plus 6 over s squared plus 9 over s. If I divide both sides by s minus 1, the Laplace transform of y is 1 over s minus 1 plus e to the minus 3s. This becomes 2 over s cubed times s minus 1 plus 6 over s squared times s minus 1 plus 9 over s times s minus 1. All right. 1 over s minus 1, no problem. That's the Laplace transform of e to the t. That's a problem. That's a problem. That's a problem. I'm going to have to use partial fractions. I'm not going to go through and do all this. I'm just going to tell you what I got when I did the partial fractions. At this stage, you should be able to get this on your own. You should verify this. So I have 3 functions, 2 over s cubed over s minus 1. And my partial fraction expansion is going to be, turns out to be minus 2 over s, minus 2 over s squared, minus 2 over s cubed, plus 2 over s minus 1. 6 over s squared times s minus 1 turns out to be minus 6 over s, minus 6 over s squared, plus 6 over s minus 1, and then finally 9 over s times s minus 1 turns out to be 9 over s minus 1 minus 9 over s. Okay, I'm not going to go through and do this because it's really tedious and long and boring, but you should be able to do this on your own, and you should be able to verify this. So what does that mean? That means the Laplace transform of y is 1 over s minus 1 plus e to the minus 3s. The 2 over s squared, s cubed over s minus 1 is minus 2 over s, minus 2 over s squared, minus 2 over s cubed, plus 2 over s minus 1. Then we have plus e to the minus 3s, minus 6 over s, minus 6 over s squared, plus 6 over s minus 1. And then finally, plus e to the minus 3s times minus 9 over s plus 9 over s minus 1. Okay, this is the Laplace transform of minus 2. This is the Laplace transform of minus 2t. This is the Laplace transform of minus 2t squared. And this is the Laplace transform of e to the t, or 2 times e to the t. This is the Laplace transform of e to the minus 6. This is the Laplace transform of minus 6t, and this is 6e to the t. And finally, this is the Laplace transform of minus 9, and that's 9e to the t. But because of this term, I have to evaluate at t minus 3 and then multiply by the step function at t minus 3. So in the end, I get y Laplace transform of that. Or that's the Laplace transform of e to the t. Then this is going to be something times the step function at t minus 3. So I'm going to have minus 2, but then I don't evaluate at t, I have to evaluate at t minus 3. Same thing here. Everywhere I see a t, I replace it by t minus 3. So it becomes t minus 3 squared. This becomes 2 times e to the t, but I have to replace the t with t minus 3. So it takes care, so that I get to take care of that term, now this term. Be careful, that's a plus. So now I'm here. So this is going to be something times the step function at t minus 3 because of that. It's going to be minus 6, but not t minus 3. And this is looking like e to the t, but everywhere I see a t, I replace it with t minus 3. So that takes care of this term. Then finally, this term is going to be something times the step function at t minus 3. There should be t minus 3 here. This becomes minus 9 plus 9 e to the t, but I have to replace the t with t minus 3. So this huge mess is my solution, my DE. And notice I didn't do any calculus. All I did was algebra. And I just have to work through carefully. I did make mistakes, but hopefully I caught them. I need to go back now and make sure that this is correct, but this is the process.